Hi, I'm Clarence. Thanks for coming to this talk. Do we have any machine learning experts in the house? Cool. Cool, yeah, that's good to know. So if I'm saying anything wrong, feel free to stop me. I graduated last year in machine learning, so I'm still new in the industry, but I've just done some research, and this is an area that I really love talking about because it sparks off lots of interesting conversation, and that's why I'm here. So machine learning, I think there's a lot of hype surrounding this area. People talk about it a lot, but not many people really know what to do when it comes to implementing machine learning pipelines and using machine learning in their specific industry. We're in the security field, so of course there's talk about using machine learning in the security industry. And there's also a lot of companies that are started based on machine learning, using deep learning, using classification as a way to detect anomalies, to detect malware. And there's a lot of interesting work in this area, but there's also a lot of pitfalls that people fall into, and that causes a lot of confusion and, gives us a lot of false positives as to whether we're actually achieving success or not in this area. So the goal of this talk is not to give an account of how you build a machine learning anomaly detector or machine learning pipeline for in a security area. It's really to give an overview of how machine learning anomaly detectors work, and to spark some discussions on when, where, and how you should use these things, and also how to exploit these systems, because these systems are far from secure, and machine learning is not something that's designed for security. Lastly, we're going to discuss where we go from here, because there's definitely lots of possibilities that we'll have going forward in machine learning and security. It's not a dead end, and there's lots of interesting developments even today. So anomaly detection and machine learning, what's the difference? I would say anomaly detection has a role to play in machine learning's timeline. There are heuristics-based anomaly detection. Just for example, you can use a rule engine, WAFs, for example. If you define an IP address access pattern, and you look at the number of requests that this IP address made to a particular web server in the last 10 minutes, and if it exceeds 10, then maybe that triggers a rule. There's also machine learning anomaly detectors whereby these rules are more dynamic, and it potentially can help catch people who are flying under the radar and making use of the staticness of heuristics to bypass your rules. So predictive machine learning is really the intersection between machine learning and anomaly detection. As I mentioned earlier, heuristics and rule-based anomaly detection has been the norm for the last 20 to 30 years, but because of how easily adversaries can bypass them, people have been looking to machine learning techniques to try to implement defenses that are less easy to bypass and less easy to capture in a single statement. Intrusion detection, for the purposes of this talk, won't be anything too specific. It's really general. Anything that can be described as an adversary trying to gain access to your infrastructure, to, for example, sending spam into your email server, committing fraud on any particular payment accounts that you own, or sending a DDoS attack into on your web server. That's considered intrusion detection for the purposes of this talk. Again, there's lots of debate to be held there, and if at any point it's unclear in the talk, feel free to stop me and ask a question. So as I mentioned earlier, machine learning has had lots of interesting applications and successful ones in the last few decades when it's seen a huge gain in popularity. Gmail popularly uses it for spam detection. This particular example that I'm showing here is one that's actually pretty difficult for a Bayesian model to catch, because it's using actually some form of ASCII art instead of just plain text. So that's harder to catch, but surprisingly, Gmail is able to catch that as spam. Also, for just any generic time series data that you see in the top right-hand corner, you can perform forecasting algorithms on them to use very simple statistical methods to alert the admin when there's an anomaly in the series. Credit cards have famously been successful with machine learning as a way of detecting fraud and when a credit card has been stolen. And again, I work for a company that tries to detect if the person on the other end of the browser is a human or a script. So that's also another popular area in which machine learning can be used. How do we find anomalies in these? Let's say you have a web server and you have a bunch of logs. It's not entirely clear how you would mine this data and generate a bunch of metrics that you can perform classification on, for example. Feature engineering is really the bulk of the work in machine learning, as many people would tell you. The actual performing of the machine learning is just maybe 5 to 10% of the work. A lot of the work is cleaning the data that you get and feature engineering. So because of how hard feature engineering is, methods that allow you to do feature engineering automatically, like PCA and feature selection algorithms, have been increasingly popular, and we'll discuss these later. So why are machine learning-based techniques so attractive compared to heuristics? For one, they're adaptive, as mentioned earlier. Adversaries can't just devise an attack strategy that flies under the radars such that you can't detect them. They're more dynamic in the sense that it adapts to the traffic, especially when you have a model that goes through online learning. Online learning in this context means that you have a model that goes through a constant and ongoing learning. So the model adapts to your current traffic. Why would you want to do that? For example, if you ran a website and the popularity changes of your website would result in changes in your web traffic model, then you want to account for these and not flag those things as anomaly. How would you account for these? You would account for these by training your model periodically, such that you would be able to get a signature of normalcy. And again, whether this signature of normalcy exists or not, we'll discuss them later. Machine learning techniques also require minimal human intervention, theoretically. That's at least the goal. But we'll see whether this actually holds or not, given the challenges that we face in this area, especially in the security field. So of course, machine learning is not a silver bullet. Many people who have read about machine learning online or have heard a lot of people talking about it seem to think that it's this magical black box that can tell you when something is going right or going wrong. I used to, in my previous project, I was working on a machine learning platform that would listen to sounds that your bicycle chain made, and it would tell you predictively if your bicycle was about to break down. And without even understanding how the actual thing worked, we had investors coming up to us and asking us, you need money for this. And we just found that really scary because obviously they weren't interested in understanding the problem, and there's a lot of hype surrounding this. I've even had founders coming up to me and say that, we actually don't use machine learning that much in our product. We rely mainly on rules, but saying that we use machine learning helps us get a lot of extra funding. So definitely something to be careful. So on the other side of the argument, why are threshold and rule-based heuristics good? For one, they're easy to understand. If something goes wrong, if a rule is triggered, you know exactly why the rule is triggered, and it's easy to reproduce. It's simple and understandable for the same reasons. And it can also be dynamic and adaptive, and we'll discuss them later. The crux is that it makes things easy, and it's easy to understand. So successful machine learning applications, let's look at some of these and see how they differ from what we're talking about today. Amazon uses machine learning for recommendation engines. Some other things that use recommendations engines pretty well are Netflix, YouTube. They recommend you things that they think you'd like by building a profile of you and matching you with other people that match a similar profile and what other people have liked. Gmail spam, we mentioned earlier, just using a simple Bayesian technique. Of course, Gmail isn't using a simple Bayesian technique today. They're using much more complex methods, from what I know. But pretty much the idea is there. This is a pretty interesting application. This came out of Stanford a couple of years ago, where it's basically doing deep learning with a recurrent neural network on a sentence, and it's able to tell you if this sentence has a positive connotation or a negative connotation. It's surprisingly and scarily accurate, and I urge you to go try it online. Just look it up, Deep Learning by Richard Socher. So we want to set some expectations for what machine learning can do for us and what it can't, in the context of anomaly detection. The idea is that, if someone were to go about formulating the problem and the solution, you want to find anomalies in data, and you want to be able to form a model of normalcy if it exists, and then you want to be able to alert the admin if anything deviates from this model of normalcy. There is a big machine learning and anomaly detection problem, and I'm not able to pinpoint exactly why this problem exists, but there's a lot of machine learning and anomaly detection research in the last couple of decades. From the 70s, 80s, 90s onwards, there have been a lot of papers written in this area. And I know because I looked them up and I tried to read through all of them, and there's a lot. But why aren't there more successful systems being used in the real world? We haven't heard of anomaly detection systems that are ubiquitous, that have used machine learning in a way that can solve a problem much more successfully than a heuristic-based one. Why? So here's my proposal. Traditional machine learning is meant for identifying patterns for learning similar things. If, let's say, in the case of a recommendation engine, you can identify patterns in how users like certain things and then recommend similar things to other users that are like them. This is the act of finding similarities. Anomaly detection is to find anomalies. And the paradox behind this is that when you're finding an anomaly, you train the negative example on a very small subset of the large positive example data space. So this is something that machine learning wasn't really designed for. And that's why when you're training a classifier and you're trying to generate this model of normalcy, it's hard. And the second thing is that machine learning is based on reinforcement learning. A lot of it is based on trial and error. So for example, when you have a large data set and you want to test out, you want to train a model to be more and more accurate over time, you rely on the feedback loop to increase the accuracy of this model. This works in Gmail by, if a piece of spam comes through your email and you see that it's spam, why is it in my inbox? You just report a spam to help improve the model in general, and that's Gmail's feedback loop. Amazon and Netflix feedback loop is more passive, but it still exists. If you don't click on the things that they recommend you, it's a negative feedback. It's a piece of negative feedback. In anomaly detection, it's hard to really pinpoint what this feedback loop actually is, because as mentioned earlier, the whole paradox is that if you can accurately and with a certain level of confidence identify what is anomalous, then what's the point of having the anomaly detection in the first place? So these are a couple of problems in a whole plethora of them that kind of illustrate the differences between using anomaly detection in the security space with machine learning techniques. So the very high cost of errors is also something that we have to consider. If a piece of spam comes to your inbox, it doesn't cost you much. It doesn't cost Gmail much, actually. It actually helps them to train their model to become more accurate. However, if an attack goes through an anomaly detector, it actually hurts the integrity of the system quite a lot because of the high cost of false positives and false negatives. If you think about it, analyst time is actually the most expensive aspect of any security company or any large organization with a security team. When you have an anomaly detector that constantly flags anomalies, then obviously analysts will have to spend a lot of human time verifying these anomalies. And what we've seen in many companies, and I'm sure you've heard of, is that IDS and IPS systems have failed in this way and have caused analysts to just turn on the mute button. Lack of training data, as mentioned earlier, negative examples have no there's just no way of generating enough negative examples to train a good enough classifier to classify something as negative. Then again, there's the semantic gap. The semantic gap, I would argue, is the one largest reason, it's the one largest challenge surrounding machine learning in general. If something is flagged as anomalous in a rule-based engine, you can verify that by running the example of the event that failed against the rule engine again, and you'll see exactly what failed. In the machine learning engine, it's harder to do so, because if something failed and you run it against the classifier model, then you know, okay, this failed, but why? Why did the classifier model evolve from its original state to the state it is today? It's harder to know, and with things like deep learning and recurrent neural networks where the internals are totally opaque to human understanding, at this point in time at least, then it's even worse, I would argue. Difficulties in evaluation. I think it's pretty hard to evaluate how effective an anomaly detector is, a machine learning anomaly detector is, just because how do you know what a real attack is? Especially in the wild, it's hard to measure the accuracy of such things. And something that we'll dive deeper into today is the adversarial setting. We'll see that actually machine learning anomaly detectors can be pretty easily and pretty effortlessly bypassed using poisoning techniques. So it's really bad if the system is wrong. When we have a high false positive rate, which means when we're flagging a lot of bots, when we're flagging a lot of non-anomalous activity as anomalies, then we're really degrading the integrity of the system. We're taking up analyst time and we're burning money for the organization. If you have a high false negative rate, maybe the rules, the heuristics are catching things that the anomaly detector isn't, then what's the point of having it? So it's very intolerant to errors, and that's different from traditional machine learning applications. Lack of training data. It's hard to clean data. If you're looking at the input logs from the web server that you saw earlier, it's not clear exactly how you would clean the data. It's not clear that when you're training a model of positive examples, you're not including anything negative in it. And that also helps adversaries when they're trying to poison your model. The semantic gap, I mentioned this earlier. So devising a sound evaluation scheme is more difficult than building the system itself, which is so paradoxical because then you're spending more time evaluating the system. And a lot of papers that, if you read about papers in anomaly detection, they're all written in a very closed environment. They all use the same 2-3 data sets from the 1980s and 90s, even papers that are written in the last couple of decades. So that's interesting. They're all always origin, destination, flow graphs, and that's weird. And I think it's because fundamentally evaluating a machine learning algorithm and anomaly detector is hard. So it's tough trying to evaluate how well an anomaly detector is just based on academic research without doing your own evaluation. Advanced actors will spend time to bypass the system, and we'll look at that later. So how have real-world anomaly detection systems failed? There's so many false positives. It's hard to find attack-free training data. It's hard to get any data at all, actually. And it's used without deep understanding. When people think about machine learning and security, they think, okay, maybe I'll just start out with a bunch of data from my web servers, from my event logs, and then I'll use maybe SciPy or scikit-learn to create a prototype. And then if I get a working prototype, then I can work off from there. But it's actually pretty hard to evaluate once you've gotten that first prototype. And that's the hard part. Feature engineering and trying to make your model more accurate, because if the model isn't accurate, then it's pointless. And model poisoning. That's also been seen in the real world. So, is it hopeless? Here, we'll spend some time looking at this problem because I'm not trying to be, I'm not trying to say that machine learning shouldn't be used in the security context. I'm just saying that if we were to use machine learning more meaningfully in the security context, then we should reconsider the problem parameters, and we should look at the problem from a different angle, that we looked at the problem from from recommendation engines, from spam filters, and from other common successful applications. And we'll go about doing this by actually looking at how machine learning anomaly detectors are built and how they function. So this is basically what we mentioned earlier. We alert if incoming points deviate from the model of normalcy. This is an example infrastructure that I got from a very popular paper that proposes a kind of machine learning anomaly detector. First of all, we have the data sources on the extreme left. And this data source will have to go through some kind of cleaning process. This cleaning process will take up lots of human time. And if it can be automated, it probably doesn't work that well. Time series construction is important because if you're doing streaming learning on this input data, then you have to construct a kind of time series that's a representation of this incoming data. You perform some aggregation on this data, and then you feed it into a model that that selects features. In this particular case, it uses PCA, which is Principal Component Analysis. Principal Component Analysis, I mean, it sounds pretty fancy, but it's actually nothing more than an algorithm that selects features in any data that you pass it. And that sounds pretty magical, and it actually is pretty magical. I'll be going into further detail on that later. But there are problems with it using this in the security space, and we'll see why. After generating features, then it will be fed into a machine learning algorithm, a classifier, threshold, top K algorithms that then generates some results for what's anomalous and what's not. That goes through manual validation, and that manual validation part is where a lot of systems fail. Then it generates the actual anomalies. So common techniques for machine learning: clustering, density-based, SVMs, neural networks. Let's focus on clustering today because it's it's the easiest to understand without getting into too much nitty-gritty details, and it's easy to visualize how this actually works. When we talk about the model in machine learning, we're actually talking about different clusters, basically a statistical representation of your data, and so the machine or this statistics actually learn what different areas of your input data are. And the ideal is that when you feed it data, it'll form clusters, and if anything deviates from these clusters, then they're abnormal. This in particular is a centroid cluster model, and it's good for online learning because, as you can see, we can keep a running model over time, and if new points come in, we can simply add to the old model. How to select features is often the most challenging problem. If you think about it, there's often a combinatorial explosion of how many features you can choose in your model, and it's always a problem between overfitting and underfitting, and also computation and space. If you have too many features to train on, you require lots of computation and time, and also you may overfit. Overfitting is a big problem in machine learning in all industries. And yeah, but isn't this just a parameter optimization? If you can iterate through all possible combinations of this, can't you just evaluate which produces the best result and just select those subset of features? So, difficulties. It's impossible to combinatorially iterate through the subset of features. It's hard to evaluate for the reasons mentioned earlier. And the notion of optimal is not clear. What's optimal? Performance accuracy is not the only criteria. You're not only optimizing for precision, you have to optimize for both precision and recall, and also interpretability, which is harder to quantify and harder to compare. Because it's a streaming model, you want to optimize for shorter training times. It has to be real time. If it's not real time, then it's kind of meaningless, because if you're doing anomaly detection in batch mode, then what's the point? You want to reduce overfitting as well. So let me just dive a little bit into PCA. PCA is a method that people use to select features automatically. Selecting features is very labor intensive. I remember I read somewhere that Yan LeCun, the Facebook AI director, once said to his grad students at MIT that one day all of you guys will be replaced by algorithms, and I'll just have a bunch of workhorses that will feature engineer for me. There will be no need for machine learning grad students anymore because all of it will be replaced by machines. And he's kind of right. Deep learning kind of does this, to a certain extent. And we're seeing that even feature engineering can be automated. And this uses statistical methods. It transforms data into different dimensions. So the list of features that it selects are actually latent. For example, if you pass in row column data in web logs that contains, for example, IP, timestamp, a URL, it returns you features that are perhaps a weighted combination of each of these fields. So they're latent and they're not obvious what they mean. This is a small visualization of how PCA works. On the left, you see the original data set on 2 axes. This data set only has 2 dimensions, so for ease of a demo. So the output from PCA aims to maximize the variance captured by any one particular dimension selected, and each principal component is orthogonal to the next principal component. It's not that important to understand the math behind this, but PCA basically does some fancy optimization techniques to do this in a computationally reasonable way. This is PCA in a 3D space, whereby if we change the model around, you see the variance captured by PC1 increases, and this organization of the principal components helps PC1 capture the most variance in the entire data set. So when we do PCA, we want to select principal components that cover 80 to 90% of the data set's variance, and this allows us to minimize the computation required to perform machine learning, and allows us to capture the most variance. Again, this is a purely statistical method, and there's no context. The PCA doesn't know whether this component chosen is an IP address or is a URL or represents a certain amount for a transaction made. So this is a scree plot. The x-axis is the number of principal components included in the evaluation, and the y-axis represents the cumulative variance captured in this model. So as you can see, having an earlier knee, having an earlier inflection in a graph means that fewer components are required to capture a lot of the data set's variance. So how do you avoid common pitfalls in using machine learning in anomaly detection? These are things that I'm proposing, and feel free to, I think that you have to understand your threat model well. Using machine learning on a statistical data set makes a lot of sense, but using the results of this model without any contextual filtering makes no sense, because machine learning doesn't know context, and you have to at least have a second layer or multiple layers of contextual filtering before you can use the results in a meaningful way. You have to keep the detection scope narrow, because it's not a be-all and end-all solution. You have to reduce the cost of false negatives and positives, however. And also, you have to close the semantic gap. This is a funny picture that I think actually happened when the two ends of the bridge didn't meet. So evaluation, there's a couple of points on how you should evaluate this. How easily can you filter out false positives? Because if your model takes into account a lot of events that are if your model generates a lot of false positives, how can you filter these out with a contextual layer? Also, evaluating true positives is important. Let's say your model performs perfectly in your evaluation process. How do you know that it's actually learning what you want it to learn? There's an interesting anecdote here that I'm not sure. It's mythical. I'm not sure if it's true because I can't find anything about it online. But it's been written about in at least a couple of papers. where the DoD in the 1980s were performing experiments on neural networks. And they wanted to be able to do some simple image recognition. At the time, it was cutting edge, because a machine taking in an image of a tank and a car, it would output if the image were a tank or a car. So the stories were that papers were written about it, and that they were very successful in these tests, and they achieved 80 to 90% accuracy in predicting, in guessing whether this image contained a tank or a car. After that, the paper was retracted because they found that if they passed in a car with a blue sky background, it said it was a tank. So you really have to understand what your model is learning, because it's so hard to understand how a model learns and what a model learns. It's not as easy as it sounds. So that's something that we have to consider when we build machine learning pipelines as well. We have to evaluate true positives. Okay. Lastly, I'll go into how we attack something like this. Why do we want to do that? We want to see how secure this is. If we're doing it for a security application, we have to fundamentally see if this fundamentally meets the requirements, the security requirements of any system that we're using in production. So how do we attack this? We want to manipulate the learning system to perform any specific attack, and also degrade performance such that people using the system can't trust it. So there's this notion of chaff. Chaff actually came from the stuff that fighter jets emit to confuse homing missiles when they're in flight and under attack. So that's something that papers have used to describe data points that adversaries send into machine learning pipelines to confuse anomaly detection systems. How would you attack it? This is a simple representation of a centroid-based machine learning anomaly detector. It's a classifier. I omitted all the points and just included the center of the centroid. So you see, injecting chaff, it's possible to shift the decision boundary of any classifier. And of course, you would shift it slowly, and the center before and after the attack would would allow an adversary to shift the model to his needs. A different kind of attack would be basically to confuse the system, and this requires a lot more volume, where you inject a lot of traffic to expand the decision boundaries such that because there's no clear attack direction, it looks perfectly normal, and traditional algorithms for detecting if a decision boundary has been shifted meaningfully will not be able to detect this. The crux of the problem is that when you're using machine learning anomaly detectors, in opposition to heuristic-based anomaly detectors, you are doing this because you want to take into account a certain kind of drift in your traffic. If your traffic were static, you wouldn't be looking into machine learning. You'll be just using rules. If you had to take into account some form of dynamic nature of your data, then you would be looking into this, and that's exactly what the attackers are using to bypass these systems. So the boiling frog attack is interesting. There are a few papers written about this, and I tried it out. Basically what it means is that to avoid detection go slow, you play around with the chaff volume and injection period, and basically you want to reduce the volume and elongate the injection period such that if you were to perform injections onto any kind of model, you wouldn't be easily detected. And this makes a lot of sense. But how would you defend against this? First thing is to maintain a calibration test set. So I'll propose a few defense mechanisms for how model poisoning can be circumvented. And then I'll go into why these don't necessarily work. So first thing is that you maintain a calibration test set. When you have the initial model, you have a test set, and you run the test set against your model, and you see and you note down which events are anomalous and which are not. And then after some time, after some period of training, you run the same test set again, and see if this has changed or not. There are a few reasons why this doesn't really work. The most important of which is that when you're selecting features, it's hard to generate a test set that exercises all of the features, especially when the features are latent. So by changing the IP address and URL, for example, you may not exercise certain latent dimensions that your model is taking into account. So this is an example of a test set whereby the green points, on the left you have the initial model, and on the right you have the updated model that has shifted, and you would see that the yellow points have fallen out of the notion of normality and the purple points have fallen in. Something else that you can do is decision boundary ratio detection. So this would mean that if you detect that a lot of points coming into your web server, for example, have been falling very close to the actual decision boundary, then you would be able to flag that as anomalous. So it's kind of like an inception of anomalies. You would have an anomaly on your anomaly detection model, and that again complicates things a lot, because how do you define how wide this region should be? It's easy to, again, for the attacker to figure out where your decision boundary ratio lies and then just fly under that, because that's static as well. So again, this allows adversaries to expand your decision boundaries. So can machine learning be secure? It's not easy, because the very notion of reinforcement learning, the very notion of online learning means that you have to adapt to the data. And fundamentally, it's hard to distinguish between real drift, real changes in the traffic that you expect, and adversarial traffic that aim to poison your model. But what you can do is to slow adversaries down, and it gives you time to detect when you're being targeted. And I think it's definitely not a lost cause. How do you defend against this? Obviously, there have been lots of papers written about how you improve principal component analysis, how you improve models to circumvent poisoning. There's this thing called antidote, and principal component pursuit and robust PCA, and these are actually in use now. Netflix wrote a blog post in February about how they're using robust PCA in their RAD anomaly detection system. I think now it's called Trainwreck. Yeah, I think, not sure, but that's in use now. But again, I did some experiments on this. I implemented PCA algorithms myself. So it's a simple toy system, and I'll be showing the results later, and we'll see that it's actually not that much more effective than the naive one, and we can still get past it with a certain level of certainty. Robust statistics is interesting. So principal component analysis measures the variance captured by any principal component by using mean. So median is a much more robust thing to use, because it's harder to shift the median of something unless you have enough volume injected into it. Also, you have to find an appropriate distribution that models your data set. A lot of research papers use Gaussian and not use Gaussian distributions just because it's easy to analyze, and there's no reason to really deviate from that notion. And because of that, a lot of libraries that implement machine learning functions also default to Gaussian and normal models, and people that don't really understand their data set well will just go with the default. And that causes a lot of inaccuracy, so it's impossible to tune, and it just generates a lot of confusion. And to use robust PCA pretty much. So I'd like to finish off with some kind of result presentation. I ran my own simulations with some real data. I didn't have access to actual anomaly detection systems that were used in other companies, because there's no commercial solutions that was ubiquitous, and I couldn't just go up to, for example, Netflix and say, hey, can I run this test on your secret system that you don't want people to know about? But if anyone wants to work with me and do future research, I'd be more than happy to do so. Basically, I looked for a large data set of Apache access logs and ran the tests that I mentioned earlier. This is a projection. Sorry, the dots in gray are a little hard to see, but basically this is just a projection into onto target flow space and the first principal component space of the data set. And we see that robust PCA and naive PCA give roughly the same direction of flow, which makes sense. This is chaff traffic injected. Again, it's not easy to generate chaff like this. I had to go through a pretty long period of trial and error because these are latent dimensions, and I couldn't just, for example, change the IP address by 1 to generate a chaff that shifted right by 1. It was hard to generate this, but pretty much it gave me what I wanted to see. Naive PCA actually shifted by a lot more than robust PCA. Robust PCA is a combination of antidote techniques and using a Laplacian distribution, which is more suited for web access logs in this particular case. So you can see the faint blue line shifted to the dark blue line, and the light blue line shifted to the darker green line. I also tested the boiling frog approaches over 10 training periods. So you can see I tried to represent the different amounts of data of chaff injected into this model with different colors. The green ones were injected first, and then the red ones were generated last. So over 10 training periods, we will see the results later, how the model changed. So the thing is that boiling frog attacks are harder to detect because people can't basically block any group of IP addresses or any characteristic of your of the method that you're using to generate this chaff by simply putting it under a threshold or saying that you're sending too much data and or maybe guessing that they're undergoing some kind of DDoS attack. And the last method of attack is simply by putting a lot of random data into this to try to expand the decision boundary. And we see that the shift is also pretty significant for naive PCA and less so for robust PCA. So here are the scree plots for RPCA and naive PCA. With no poisoning, robust PCA performs pretty well for that particular data set. With the boiling frog attack over 10 training periods, we see that it performs also pretty well, but there's a lower chance of detection on the adversary side because they won't be that easily detected as a DDoS attack or someone trying to poison their model. We see that RPCA with 50% chaff, so it means that 50% of the total traffic that you're receiving is adversarial traffic. It actually degrades the integrity of the system quite a lot, and it almost nears the effects of a random detector. So just jumping ahead to evasion success, let's look at these numbers. So naive chaff injection with naive PCA gives you 76% evasion success. So that's pretty bad. With boiling frog injection, it gave you 87% evasion success. But even when you're using both boiling frog and robust PCA, it gave the adversary 38% evasion success, which in my opinion is still pretty high. If you're able to attack an anomaly detector and evade it with 40% accuracy, I'd argue that the anomaly detector isn't working as well as it should. So that's it. Anomaly detection systems today are not so good, but they're improving. I think machine learning still has a role to play in the security space. They're still vulnerable to compromise, but obviously there still is a lot of research being done in this area. And if we can find more robust ways to perform classification, to perform feature selection, then that'll be great. But in general, the wisdom surrounding this area is that you should use machine learning to find features and thresholds, and then use these selected features to write heuristics, and then run your anomaly detector with these heuristics. because then you'd be less susceptible to online model poisoning attacks, and you'd be less and you'll be able to understand what caused these attacks, what caused the anomalies better. So what next? I want to do more tests on anomaly detector systems that others have created. If you or your company or a friend has implemented any anomaly detection systems and wants to work with me to test them out, to see how susceptible they are, how secure they are against model poisoning, against any other kinds of attacks, then that'll be great. Defenses against poisoning techniques. I mentioned a couple earlier, using the decision boundary ratio and using chaff detection. If there are better ways to detect if someone is trying to poison your model, then obviously that will help the cause a lot. And also, I want to experiment on more resilient ML models. There are a lot that are in research in the research phase today, and I think in the coming years they'll be much more popular if they show promise. Lastly, I'm not sure how many of you guys are from the SF Bay Area, but I run a meetup group called Data Mining for Cybersecurity. It's a pretty active group. We have meetings between 2 to 4 weeks, once every 2 to 4 weeks. Our last one was actually last week at Area 1 Security, and our next one is at Netflix. So we talk a lot about machine learning and using statistical models, using data mining to solve security problems. And it's an active area of research. There's a lot of talk on it. But what I've seen is that people want to go about using machine learning in their security problems, but they don't know how to start. And if they have started, it's more of a prototyping thing, and they haven't found enough cause to switch over. Our last meetups were at Facebook and LinkedIn, and I work for a company called Shape Security. And what we do is we detect automation in web traffic. So that's it. Any questions? Here. Okay. The question is whether the lack of effectiveness in machine learning techniques in anomaly detection is more due to the lack of training data or the ineffectiveness of the algorithms to detect these anomalies. It's hard to attribute how much each reason causes a failure point, but I think that the data fundamentally needs to be there in order to tune any models. If we can't get any data, then we can't tune the models and we can't tune the algorithms to make the model better. So fundamentally, personally, I feel that the lack of training data is a big problem, because if we're doing data mining, we need data. So to me, that's a larger problem. Yeah. Right. Right. Um, I agree with what you said fully. I think there is a problem with using out-of-the-box machine learning in security applications because of what I said in the earlier. Um, I think there are promising applications of machine learning in security. There is I think that there's a paper written a couple of years ago whereby malware and Android applications were successfully found with up to 95 to 97% accuracy on their test set, of course, using deep learning techniques. And that's interesting because malware detection using machine learning has been pretty established for a while, and it's a small enclave in which machine learning has shown success. But in a more generalized approach, where we're talking about, finding anomalies in general without any context surrounding it, then I think, personally, I'm pessimistic. Until something new comes up, then we have to reconsider the problem. Yeah. 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 Yeah, exactly. I think I can't say I know exactly how that Android malware thing worked because it's been a while since I looked at it. But if I remember correctly, what they were doing was to train the model on a bunch of malware that it has seen before, and have a test set containing malware that it hasn't seen before. So it used a recurrent neural network to train a model of normalcy and a model of abnormalcy, and then the model was soft enough, had a soft enough decision boundary ratio that was able to classify something that it hasn't seen before, a totally different kind of malware or weird function calls, API calls that would let it classify the application as malicious. Yeah. Yes. Yeah. So right, that's a great point. So the scenario that I created was a really a toy scenario, in which I got a whole bunch of web logs, and they were all timestamped, and I just fed them in over a simulated training period. So I didn't run it over, let's say, a week. I ran it over a short amount of time, and I simulated the changes in time. And so the training Yes, so the chaff had an immediate effect. And the problem of the boiling frog attack is really more complicated than I actually made it sound earlier, because the adversary really has to have knowledge of when you're training a data set. Presumably, the model won't be trained continuously 24/7. It'll be trained, commonly seen scenarios are it'll be trained once a week, maybe every Sunday at 5 o'clock. It'll be trained for an hour, and then this would be the model for the coming week. So if the adversary didn't know when the training occurs, or if you randomize the training period, then it's theoretically more easy for you to detect if someone is sending weird sources of is sending weird traffic to your endpoint. But then again, you know, we have to assume that the attacker has a level of knowledge that you are not expecting. Yeah. Mm-hmm. Yeah. Right. That makes sense. Yeah, I agree. Cool. It's good news. So, just looking, I haven't looked at all kinds of algorithms, obviously, but oh, okay, yeah. Sorry, we have to wrap up after this. But I've seen that classifiers are particularly susceptible to poisoning attacks and are maybe the most insecure because they use the notion of the means of sets of points, which is insecure statistics, and using SVMs would be helpful. I think I haven't played around with testing it too much, but just it sounds like it would be perform better against attacks. Okay. Yeah. Oh, got it. Thank you. Thanks so much.
Great talk. I'll be one of the meetups.
Yeah, thank you.